Hello, my name is Darren Holmes, and today we're going to be using the Primer Trainer to look at lesson number 2, running your first program. Please make sure that you have completed lesson number 1 before you start lesson number 2. So at the start of each lesson, you can see that they post the new instructions that you're going to learn about. You notice this instruction is in the format of in byte, and the opcode for the instruction is dB. We have an out byte, the opcode is D3, and a jump address, and the opcode is C3. So looking at page 35 of the 5th edition of your textbook, you can see section 2.2.1 talks about the 8085 instruction set. And section 2.31 talks about an introduction to word size. So what they're saying here is the 8085 instruction set is classified into the following 3 groups according to word size or byte size. So we can have a 1 byte instruction, which is just the instruction. We can have a 2 byte instruction, which usually has an instruction plus some kind of data. And we can have a 3 byte instruction, which is usually an instruction followed by a memory address location, which, as we know, takes up 2 bytes. So an example would be something like FF01 is actually 2 bytes because it's 8 bits. So we have the 8 bits for the instruction, or we have the 8 bits for the instruction plus 8 bits of data, or we have 8 bits for the instruction plus 16 bits for the address. Now Appendix F in your textbook, that's somewhere around page 737, they give you the 8085 instruction set. So you can see on page 752 they have the in instruction, which is to input data to the accumulator from a port with an 8-bit address. So the opcode for it is in, and we have an 8-bit port address. So this is a 2 byte instruction. It takes 3 machine cycles and uses 10 T states. The hex code for the in instruction is dB. So they give you a complete description of the instruction. They tell you what flags are affected, and they give you some comments that are worth reading. So they have the out instruction, which is output data from the accumulator to the port with an 8-bit address. Once again, we have the opcode. The operand is the 8-bit port address, and again it takes up 2 bytes of code. The hex code for the out command is D3. The last command is the jump unconditionally command. Its opcode is JMP. The operand is 16 bits. So this is a 3 byte instruction. It takes 3 machine cycles and 10 T states to complete. The hex code for the jump instruction is C3. As you can see, they give you an example here. They're using memory address 2000. We use FF01, 02, 03. They start at 2000, so 2001, 2, 3. So the code is C3, and that's the jump location, and they're jumping to 2050 in hex. So you notice the 50 is entered first and the 20 is entered second. So you should have a couple of questions by now. The first question is just how many instructions does the 8085 contain? Well, on page 776 we have the 8085 instruction summary in hexadecimal order. So we know it's going to be 8 bits wide. So it starts at 0, 0 and finishes on the next page at FF. So 0, 0 to FF is actually 256 different commands that the 8085 recognizes. Now while you're thinking 256 instructions are a lot for you to memorize, I just want to jump ahead to lesson 3, where we're going to use the move immediate instruction. So the move immediate instruction is able to move immediately something into the A register, or something into the B register, something into C, something into D, something into E, something into H, and something into L. While each instruction has a different opcode, you notice they all have the move immediate component to it. So you just have to remember that you're moving something immediately into one of the registers. So there's 1, 2, 3, 4, 5, 6, 7 commands grouped together as move immediate. So this makes it a lot easier for us to memorize what all the instructions are for the 8085. So the next question you should have is, what the heck is a T-state? Now to answer that question, we're going to open the Primer Trainer Self-Instruction Manual, and I'm using Manual Revision 2.5. So this is page 8 of the Self-Instruction Manual, where they talk about schematic page 1 and the microprocessor. So buried in all these words of wisdom is the system clock oscillator, whose frequency is set to 6.144 megahertz by crystal Y1. So that's the frequency that our primer trainer is running at. But reading further, it says the oscillator signal is divided by 2 within the 8085, and this signal is now the main system clock, referred to as sys clock. It says all timing of the microprocessor operations is driven by sys clock, which in our case is 3.072 megahertz. The next thing that we need to read is each pulse of this clock signal is called a T-state when referring to operations internal to the 8085 and its buses. So a T-state is the time it takes for one pulse of the clock signal, which is 3.072 megahertz. So 1 divided by 3.072 megahertz will give us the value of a T-state. So I just want to refer you to page 104 of your textbook, and it says now we can define 3 terms: instruction cycle, machine cycle, and T-state. So instruction cycle is defined as the time required to complete the execution of an instruction. The 8085 instruction cycle consists of 1 to 6 machine cycles, or 1 to 6 operations. So a machine cycle is defined as the time required to complete one operation of accessing memory I/O or acknowledging an external request. Okay, this cycle may consist of 3 to 6 T-states. And a T-state is defined as one subdivision of the operation performed in one clock period. These subdivisions are internal states synchronized with the system clock, and each T-state is precisely equal to one clock period. The terms T-state and clock period are often used synonymously. So just to recap, our crystal is 6.144 megahertz. The CPU divides that by 2, so your system clock is 3.072 megahertz. One T-state is equal to 0.3255 microseconds. And when we looked at the jump instruction, it takes 10 T-states to complete. So the jump instruction actually takes 3.255 microseconds to complete. This is important if you're trying to create a timing delay loop You need to know how long each instruction takes so that you know how many times to repeat those instructions. So our next question is, why does the CPU divide the crystal frequency by 2? To answer that question, we're going to look at a very old document. You can see it's dated October 1979. This is the Intel MCS 8085 Family User Manual. So looking at section 2.2.6, the internal clock generator, we can see we have a line here representing the outside of the 8085 where the crystal is connected and the clock output goes. So the crystal actually comes in through a Schmitt amplifier, and we know that Schmitt will clean up a signal because it works on voltage levels, and that goes into a T input on some kind of flip-flop. And we can see that it's edge triggered, it's negative edge triggered, so every time it receives a negative edge, the cue becomes the opposite of what it was before. So if it was 1, it's now 0. If it was 0, it's now 1. So this flip-flop is just toggling every time it gets a negative transition. So that means the output frequency is going to be half of the input frequency. Also note that we're using the Q and the Q naught. So internal to the CPU, something is happening on the positive half of the clock cycle and something's happening on the negative half of the clock cycle. So we'll cover that later when we investigate further the internal workings of the CPU. So one last question you might be asking is about the crystal. Why is it an odd number? Why isn't it exactly 6 megahertz? Why are we using 6.144? The answer is the CPU divides that signal by 2, generating a system clock of 3.072 megahertz. Now when you divide this by 320, you come up with 9.6 kilohertz exactly. There's no rounding errors or anything. It's exactly 9.6 kilohertz. And our UART is going to transmit data to our computer at 9600 baud rates. That's 9600 bits per second. So the timing between the primer trainer and your computer has to be exactly right on. So by using 6.144 megahertz, it divides evenly to generate that 9600 baud rate. So I just wanted to show you that each of these lessons are not self-contained. You'll need the information that's contained in the primer self-instruction manual, as well as the theory contained in your textbook in order to complete each of these lessons successfully. So looking at lesson number 2, we can see that they've listed new instructions that we need to understand. So when we're looking at instructions, these are the mnemonics. Those are for the human to understand what they're doing, and it has to be converted into an opcode. So we've seen the in instruction before, and we've seen that it is the opcode DB. So the DB is what we loaded into memory, and that's what our central processor, or our 8085, understands as an instruction. DB has no meaning to us, so we've used the in mnemonic to represent DB. Now the in instruction is followed by a byte of data, and when we entered our program in lesson 1, we said DB12, so 12 was our port that we were going to get the data from. So we say in 12, and the computer sees DB12. You notice we've got the out instruction followed by a byte of data, and the out instruction is D3, and the byte of data that we used was 11. And then we're going to use the jump instruction. So the jump instruction is C3, and then we jump to an address. Now the address is actually 2 bytes in length, So when you look at the program, it's going to say 01FF. So we put the least significant byte first. So they're giving us the assembler program here, and if you've completed the C course, you know that we take our C language and we have to compile it into machine code so the computer can run it. Here we're taking the assembler program, and this is human readable code, and we have to assemble it into machine readable code. So up here we're saying the LEDs equal 11H. So when we say we want to output to port 11, we're outputting to the LEDs. And we want to input from the dip switches, that's equal to port 12. So you can see here, the first thing we're going to do is use the org command, and we're orging, or the origin of our program will be at FF01. We're going to take an input from our dip switches, so that means we're going to load a register with the dip switch values. We're going to output these to the LEDs, so we're going to output the A register to the LEDs, and then we're going to jump to loop. So loop is back here where we have the in instruction, and the in instruction is at origin FF01. So when we convert this into machine language, we can see that FF01 contains DB, and DB is the in instruction. FF02 is 12, so 12 is the port address for the dip switches. FF03 is D3, which is output, and FF04 is 11. So 11 is the LEDs. FF05 is C3, and C3 is the jump instruction. And we're going to jump to FF01, so the 01 gets loaded first, followed by the FF. The computer internally knows to convert this to FF01. So if you haven't entered the program in from lesson number 1, I recommend you go back and review the lesson 1 video. I'm going to assume that you have loaded it into memory. So to run the program, we press the reset button, and it brings us back to FF01. And then we press the function and the run key. You'll notice nothing is being displayed on our 7-segment displays except for the word function. All my switches are in the up position, so if I was to move one of my switches to the down position, you'll notice the first LED comes on. So as I move each of these dip switches one after another, you'll notice it turns on the next corresponding LED. If I go right down to the last switch, it will turn on the last LED. If I move the switches back to the up position, you'll notice it turns off the LEDs. The program is continually running. It does the input from the dip switch, the output to the LEDs, and then jumping back to the start position again. To stop our program from running, we have to press the reset button, and that will bring us back to FF01. The primer trainer also has a single step function. So to illustrate this, I'm going to hit the reset button, and it brings us back to FF01. And I want to put some data on my dip switch, so I'm going to put the first 2 switches down, the next 4 switches up, and then the last 2 switches down. just so that I have some different data in there. And then to single step, you don't press function run, you just press the run key, which also does a single step. You notice it increments the program counter to FF03. That's because at FF01 we have the DB, or in instruction, followed by a byte of data, which was 1, 2. So the next actual command is stored at FF03. Now notice there's nothing coming out on the LEDs at this particular time, but I can check what's in the AF register pair by pressing function and the A key. So you notice in the accumulator, or the A register, the data is 3C. So 3 is 0, 0, 1, 1, and C is 1, 1, 0, 0. So you can see our dip switch, when the switch is down, that's logic 0, and when the switch is up, it's logic 1. Pressing the enter key brings me back to FF03, and when I press the step key, it outputs the contents of the accumulator to the LEDs. And that instruction was out 11, or D311, so the next memory location for the next instruction is at FF05, and you can see that's displayed in the address register pair. The next instruction is C3, which is the jump instruction, so if I press the step key, it now jumps to FF01. I'm going to change the data on my dip switch, and you'll notice there was no change on the LEDs because it hasn't actually entered that data into the accumulator yet. I have to go to the next step. It's now entered the data into the accumulator, and you can check it by pressing function A. So if I hit the step key again, you notice the data has now changed on my output LEDs. If I press the step key again, it goes back to FF01. And if I hit the step key again, it goes to FF03. So you can step through your instructions and it will continually loop through the program as you had expected it to do. So at FF01, if I press the step key, it loads the data from the dip switch into the accumulator. So if I press function A, that is now the data in my accumulator. I can now change that data, so I'm going to change it to 1, 2, and put 0, 0 into the flag register. If I press enter, I now press the step key. It will now do my out 11, and you notice it was the data that was in the accumulator that is output to the LEDs, not the data from the dip switch, because we have took the data from the dip switch, entered it into the accumulator, then changed the contents of the accumulator, so now we have a different output on the LEDs from what we had in our dip switch. Now in the instructions, there's a very important note. It says the primer was designed so that the digital output LEDs will turn on when a logic 0 is output to a particular bit of port A. So with your program running, you'll look at my dip switches and see they're all in the logic 1 position. So if I move the first switch down, my LED comes on. So entering a logic 0 turns the LED on. So if I examine what's in the A register, you'll notice the contents of the A register is F, E. So F is 1, 1, 1, 1, and E is 1, 1, 1, 0. So that last bit, being 0, actually turns the LED on. So using the primer simulator, we'll review what we've accomplished on the EMAC Primer Trainer. We'll start by turning on the primer simulator and verifying that we have loaded our program into memory. We'll hit the reset button and we'll press function and run. Now remember, we cannot activate the sliders on the dip switch, but there is a little button underneath to activate that switch. And you'll notice when the switch is in the down position, showing us logic 0, we're outputting a 1 on the LED. So you can verify this with the other switches. To stop our program from executing, we can hit the reset button, and it takes us back to FF01. We can use the step key to step through our program. So it's done the first instruction where it should have loaded the data from the dip switch into the accumulator or A register. We can examine that by pressing function and the AF or A key. And you can see in our accumulator is FE. That's 1, 1, 1, 1, 1, 1, 1, 0. We can change that value. We can change it to 0, 1. And then remember, we have to move it over. So 0, 0. So now the 0, 1 is in the A register. We can press enter. We're now at FF03. If we step through our program, it outputs 0, 1 on our LEDs. And remember, our LEDs are going to output the opposite of what we expected it to be. So if we output a logic 0, the LED is on. And if we output a logic 1, the LED is off. So our primer simulator seems to be working identically to our primer trainer for lesson number 2. So this concludes lesson 2. In lesson number 3, we're going to be loading registers and transferring data between registers. So please subscribe so that you don't miss any of our lessons.